Welcome to the second presentation in the third webinar series presented by the International Absorption Society. The IAS is an international organization dedicated to advancing absorption as a solution to scientific, engineering, and human welfare challenges through the promotion of absorption research and education. We hope that all of our attendees, their families, and colleagues are safe amid the ongoing COVID-19 pandemic. We thank everyone for attending the webinar today. The webinar series has been an immense success. The recordings of previous webinars continue to be viewed on YouTube. This is the second webinar of our third series, which we will continue to have monthly throughout the year. We tend to continue with a variety of speakers from industry, academia, other research institutes, as well as PhD students and early career researchers. Announcements regarding the third series will be distributed through the IAS mailing list and the IAS Twitter feed. Today's webinar will be given by Professor George Shimizu at the University of Calgary. I am Nicholas Wilkins at the University of Alberta in Canada. Today's webinar will be moderated by David Donacci at Imperial College London in the United Kingdom and Nicholas Krenti of Rutgers University in the United States. We are required to remind attendees and future viewers that the views expressed by the speaker, host, or other moderators are not necessarily those of the IAS or the institutions associated with those individuals. We ask that you consider joining the IAS as a regular member if you are not already. Our dues are minimal, only $20 US per year, but support the publication of our flagship journal, Absorption, contribute to travel grants and workshop seed funding for IAS members and affiliated groups, as well as aid the organization of our triennial conference on the fundamentals of absorption. Members also receive free access to IAS supported materials, including our journal, as well as the absorption database published by Springer Materials. The membership renewal for 2022 began in October, and any payments after this date will apply to 2022. Anyone can follow the IAS on Twitter at @adsoats for future updates regarding IAS events, webinars, and information about scientific meetings. Please help us expand our YouTube channel by liking this video and subscribing. The IAS will host the 14th International Conference on the Fundamentals of Absorption in May 2022 in Broomfield, Colorado, near Denver. The conference will cover all aspects of absorption, ranging from fundamentals, process applications, green energy, and among others. Beyond the scientific content, the setting is outstanding, just downhill from the mountains of Western Colorado, which will allow for excellent side trips and excursions. Abstract submission is now closed. Registration information will be available online, and an official opening for registrations will be announced in the first months of 2022. I'll now hand it off to David Donacci, who will moderate the Zoom Q&A.
Thank you very much, Nicholas. I also have the pleasure of introducing our speaker today, Professor George Shimizu. George Shimizu is originally from Winnipeg and received his BSc from the University of Winnipeg in 1989 and completed a PhD from the University of Windsor in 1993. He was an NSERC postdoctoral fellow at the University of Birmingham and a research associate at the Stacey Institute of the National Research Council before joining the University of Calgary in 1998. He is currently a professor at the University of Calgary and leads a group that explores metal organic frameworks for multiple separation and proton conducting applications. He has received many awards, including the Rio Tinto Alcan Award from the Canadian Society for Chemistry and the Alberta Science and Technology Leadership Award. During the webinar today, questions can be submitted to the speaker in two ways, via the Q&A tab for those joining in Zoom, or as comments on the YouTube live stream. Nicholas Krenti will forward those comments to Zoom, and I'll moderate those for George today. With that, I'd like to hand over the floor to George.
All right. Thank you to Arvind and all the other organizers. And let me share my screen. All right. Good morning or good afternoon or good evening, I guess, depending on where you're watching from. And let me just get right into my whole presentation is going to be about one material, just that we call CAF20 for Calgary Framework. And this, we were fortunate to have this published late last year in Science. But before being published in Science, it was the subject of 2 patents. And I will do a declaration that I have a financial interest in the material, and I do receive licensing royalties from this compound. So just to begin, just a slightly broader picture on carbon capture. There was a wonderful report that came out in 2017 by the Mission Innovation Group, which is to advise many countries globally on clean energy, and in particular, carbon capture, utilization, and storage in this report. But for the solid sorbent community, some of the main highlight items were that 2 of the 8 priority recommendations where it was important to design tailor-made materials, but equally important was to integrate those materials into the appropriate process. And this will be a very common theme that will almost become redundant by the end of the talk, and I hope so. It is a line of thinking that's become increasingly recognized, and a lot of very nice recent papers have come out where basically the main point is you can't really extrapolate from a very simple molecular metric like how much CO2 does something take up to is it really going to be a useful compound in a large scale process. And so I've just borrowed a very nice figure here from a recent paper from Marco Tata and Camille Petit. And it's all these are excellent works. So at the risk of being more exclusive than inclusive, here's a list of papers to consider. Right, so I think everyone has seen a list like this before when you talk about what is the wish list for a solid sorbent. And some of them are quite obvious, like the CO2 capacity, CO2 selectivity, but we also want kinetics, we want mild regeneration. Something that's less done, excuse me, at least in academic studies, is to actually bridge to the engineering and make structured forms of these. And then ultimately the stability, not just of the material, but of the structured form, and then the ability to make this on a bigger scale. So what is CAF20? CAF20 is zinc triazolate oxalate. So it's just dimers of zinc bridged into a layer by 1,2,4 triazolate, and then those layers are subsequently propped apart by oxalate anions. And I've got pictures of the main contributors as we go along, but Vaidya is now a very successful professor at ISER Pune, and Janvin is the X-ray facility manager at Memorial University. So really, the key things to take away from here, there's a lot of metrics here that I think in terms of the MOF community don't really stand out as anything particularly noteworthy. 38% void volume, roughly 500 meters squared per gram surface area. But the pores are quite small, and the pore size here is actually critical. The other thing to note is that there isn't a dominant binding site There's no polarizing functional group. There's no open metal site in this compound. So the binding interactions with guests are only through dispersive interactions. So here is the CO2 and nitrogen isotherms, again, much like what you're accustomed to seeing. I will say, as a benchmark, the heat of absorption, I should say heat of absorption here, matches that of the benchmark zeolite for carbon capture 13x very, very well. In fact, the heat of absorption is the same. And at the given temperatures, the shape of the isotherms actually come very close to overlaying. The selectivity based on just comparison of the single component isotherms, we get around 230. And if you do 293, 373 K swing, you get a working capacity of about 1.8 millimoles per gram. Now, having said that, a common theme I'm going to mention here, the title of the talk is De-risking Adsorbent. And again, a common theme will be you really need to engage partners up the technology ladder. And so what can you do to de-risk it as much as possible to make it worth their time and effort and funding to be engaged in the project? So first, an easy thing to do is just check the thermal stability. So this is just cycling alternating between CO2 and nitrogen, going 50 cycles, swinging between 40 degrees and 110 degrees, and reintroducing carbon dioxide and showing that the capacity is retained. We can go a step further. Water stability was very good, so we went to steam and just showed that the powder X-ray patterns, and you can reproduce the nitrogen isotherms as well afterwards. We found references to help us generate wet SOx and NOx in the lab. And so again, after those, we see the same powder X-ray and retention of the gas absorption. Now, at this point, we have something with CO2 uptake equivalent to the benchmark zeolite, and we have good stability. And a very reasonable question from the zeolite perspective would be, well, really, who cares? Because in all likelihood, the moth isn't going to be as scalable or as cheap as the zeolite. And so really where things become much more interesting is when we start to look at the water absorption. So this is the water uptake of zeolite 13X, and this is the water uptake of CAF 20. So we see not just a dramatically lower capacity, but really importantly, at lower partial pressures of water, the material, the isotherm shape is showing some hydrophobic behavior. We did heats of adsorption. So these are just extracted from the single component isotherms. And again, at zero loading, we calculated a very low heat of adsorption for water. This was actually reproduced by Tom Wu, who I'll introduce in a second, in terms of modeling the water uptake of this compound. So this is very interesting because this is just a physisorptive material. So you really don't expect CO2 to have a higher affinity than water, just based on the fact that water is just a much more interactive molecule with everything. So Tom and his students Jake Berner and Hannah Durakova carried out a suite of very reliable calculations. So modeling the CO2 binding site, but also the heats of adsorption. And again, what we see at very low humidities, that CO2 has he modeled a higher binding energy than for water. Of course, ultimately, water will attract water and the pores will fill. So what about some actual experimental support then? So showing that the water isotherm looks hydrophobic, doesn't really mean much in the absence of a competitive experiment. So this was wonderful work done by Arvind and his PhD student, Tai Nguyen, who is now employed at SANTE. So just for maybe the odd person in the audience who might not be familiar with looking at a breakthrough curve, let me just explain. So this is just in units of dimensionless time, so the time it takes for a non-interacting species to pass through this column would be. So here, what we're seeing is nitrogen passes through sooner than CO2. Nitrogen breaks through, and then the CO2 breaks through. And what you see is as the CO2 concentration is lowered, the breakthrough of CO2 is progressively later and later because it takes more time to saturate the column. But this type of breakthrough curve profile is very indicative where you have highly selective binding of the heavier phase over the lighter phase. So this basically is showing very good selectivity for CO2 over nitrogen. The figure here on the right, I just wanted to show that the area behind these curves is quite significant because that actually represents, if you factor in the flow rate and the void volume, this actually represents the volume of that column that is occupied by the particular fluid phase. So here again, later breakthrough, but the total area here would be converted to a volume. So again, we're seeing good retention of the capacity. So that was for CAF20. So this is CO2 and water on zeolite 13X. And so what we see here is a similar type of curve to what we just saw for CAF20 CO2 nitrogen, but now water is the heavy phase. And so this curve is, well, zeolite means boiling stone. So not surprisingly, the water retention is much more selective than the absorption of CO2. When we do the similar experiment, when Arvind and Tai did the same experiment with CAF20, this is what we see. So we see a completely different profile. And I mentioned Farid here because Farid also did it. They're not depicted here, but a series of very nice breakthrough experiments. What we're seeing is a completely different profile. And it seems as we vary the relative humidity, the breakthrough times are not highly impacted. So here, this type of profile between the CO2 and the water, this actually corresponds to a very competitive binding between the CO2 and water rather than dominant binding of the heavy phase. So I think a more compelling illustration of this is actually the water breakthrough that Arvind and Tai did. So we'll just start by looking at the figure on the left. So this is the water breakthrough in air. And then when the carrier gas is switched to carbon dioxide, the water breaks through dramatically sooner. And if you vary the humidity again, you see the expected trend in that the water is breaking through earlier, but to a lesser extent. So remember, the area behind this curve corresponds to the volume of the column that's occupied by that fluid phase. And so in these cases, these yellow areas, this represents the volume of this column that used to be occupied by water that is now occupied by carbon dioxide. Now, if you consider this in the light of, this is a physisorbent with negative 39 kilojoules per mole heat of absorption, and that CO2 boils 157 degrees lower than water. This is quite a remarkable observation. The plot on the left basically summarizes an entire series of those experiments at different relative humidities. And I think if there's one key experimental figure for this entire work, it's this paper. It's this figure. So what we're looking at here is the green plot represents the water uptake by CAF20 in the absence of CO2. The red plot represents the uptake of CO2 by CAF20 as a function of relative humidity. So again, up to about 35–40%, you're getting most of the capacity, even up to 60%, it's still over a millimole per gram CO2. But this blue plot is the water isotherm in the presence of carbon dioxide. So again, we're not just binding CO2 in the presence of water, CO2 is being bound and suppressing the water absorption, right? And this will become really critical in terms of the benefits to the engineering incorporation. The figure on the right is just as a comparison for zeolite 13X, similar experiments. And I'll just show the CO2 plot here. So first of all, the scale on this plot has to be changed to be logarithmic, just to actually get down below at 2% relative humidity. We're down here. Okay. So back to Tom Wu's modeling. So I mentioned he had modeled the binding site of the CO2 in CAF20. And I said CAF20 didn't have any dominant individual binding site, no polarizing functional group. The main binding site is simply right in the middle of the pore. And there are 3 weaker dispersive interactions, but that cooperatively can give you 39 kilojoules per mole. So where does water go? So first of all, water modeling is a big challenge, much more challenging than CO2 or methane. So the plot here is just to show the fidelity that we have with the faith and fidelity we have in Tom Wu's modeling. So in terms of modeling the experimental isotherm, he captures the capacity that we see, and he captures the step, the position of the step in the isotherm. Okay. So when the molecular dynamics simulation is run, as I mentioned, once water goes into the CAF20, water should actually be the favored binding site, the pore that actually has water. So when the MOF is actually half full of water in the simulation, you have pores that are either filled or pores that are empty. So initially we thought this wouldn't explain the suppression of water though. So for that, Tom had to do the competitive measurement. And what we saw there, so is that basically the binding sites of water, this is a hierarchy of water binding sites in this pore. Water goes more to the corners, whereas CO2 goes more to the middle. When water comes into the structure, as I mentioned, the favored pore is the one that already has water in it. But CO2, with the 3 binding point interactions, can actually sit in the middle of the pore, and the next water is actually only looking to form a single hydrogen bond. So the CO2 binding will actually impede the binding of the next water molecule in the same pore. And so we're quite confident that's the basis of the water suppression. So where are we to this point? Let me just do a midway summary. So we knew at this point that CAF20 really had benchmark stability. It has a good CO2 capacity and selectivity despite a modest heat of absorption. And what was really interesting was that it could actually outcompete water up to 40% relative humidity for binding. We were excited that it could be made in a single step. And I have to say, I really underestimated how big a deal it was that the single step would be solvothermal. At this point, we were already trying to commercialize this material. And the hurdle at this point was really the scalability, even though it was a single step from commercial compounds. So what do you need to move forward from this point? Well, so here we are in our lab, and the next step is a structured powder. So Arvin's experiments were done on extrudates, but in terms of structuring, you can optimally structure for a specific process, which is really getting to expertise in complex fluid dynamics and really making a highly optimized structured form, whether it be a laminate, 3D printed material, what have you. So that has to be done in synergy with whatever the engineering manifestation to be incorporated into is, whether this is going to be a pressure swing, temperature swing, and then ultimately this needs to be deployed at some emission site. And this, even this 4-panel doesn't tell the whole story, because you still have to account for the fate of the CO2. So I just want to spend a minute on this slide then, because it's really important, and in terms of some of the challenges we had in engaging partners upstream. So a lot of times, and I can't generalize here, because really it depends who you're talking to, even from any potential partner, depending on what different individuals' horizons are in terms of their working goals. But a lot of times it seems people, as far as carbon capture, are really looking for an easy answer, and there really isn't an easy answer. I think it needs quite an in-depth analysis before you can really decide whether something's going to be the best material for you. A lot of times, if there is infrastructure, it can be on quite a large scale. And in those cases, sometimes people are looking for a drop-in solution. And again, this is for someone who might be working at a gram scale, where your first demonstration requires several tons of material. That's not a gap that you're going to be able to bridge. Even in terms of, again, going back to this word derisking, it's very difficult sometimes to gain knowledge of what specific process streams are in industry. And so, how can you address whether your material is the best when you're not even sure of the specific problem? And even, we can say post-combustion, but there's so many different streams even within that, and water ratios, acid-gas concentrations. Here I say less valid comparisons. In some conversations I'd had with people up the technology chain, one point that was mentioned was, well, we'd like to compare apples to apples. And so what was often given as a benchmark was the cycling conditions for monoethanolamine. And they wanted to know, how would this perform under these conditions? And they thought, well, by giving this as a caveat, it is you're getting an apples to apples comparison. When in reality, why would you pick the conditions that are optimized for a chemisorbent liquid when you're comparing to a physisorbent solid? And so in the end, it's about as far from an apples to apples comparison as you could have. Okay, so if you really want to do a valid comparison, compare the optimized process for each individual sorbent. Another issue is what is the scale of the viable investment? I sort of touched on that a second ago. But when there isn't infrastructure already in place and something new needs to be built, I did have a conversation once with a potential industry partner, and I was told if it isn't 10,000 tons a year, it's not worth building. And that's a very fair statement from their side, but I think it's something that often someone, again, when you're making a gram of material, it's a pretty big gap to try to bridge. And again, even I've had conversations with people where even if you could bring a skid, which we're not typically, to an emission site, they also expect you to bring a pipeline to take away the CO2 to a sequestration site. So if you're at this stage, don't underestimate how many partners you're going to need to go forward. So having said that, in Canada, we have a wonderful partner. Oh, but first, let me just explain a little bit more on the structuring, because quite a bit of effort was put into that, both in Arvin's group and by Farid Akhtar in Sweden, and one of my PhD students, Nick. But I'll just say CAF20 structures very well, and I'll move on from here. So as far as our Canadian partner, SANTE is a carbon dioxide company out of Vancouver, and they have two priority areas. One is taking powders and making very interesting structured forms of them, and the other is implementing those into, again, a proprietary engineered form that they design. So if you've not heard of the SANTE system, let me just give you a quick description. So the engineering, so this thing that looks like a big cheesecake here is actually where the moth would reside. And so the capture is by flue gas entering the bed, CO2 being captured, and then this bed rotates. So the capture is physisorptive here, the wheel rotates, and this is where I think the SANTE system is really unique, is that the CO2 removal, the regeneration of the bed, is done by direct treatment with steam. So it's not a conventional temperature swing. It's more of a concentration swing, because at 100 degrees, CAF20 still takes up a decent amount of CO2. But when you're actually treating it with steam at just over 100 degrees, you're actually sweeping out all the CO2. So the working capacity is the entire amount of CO2 that was captured. Then this goes on to the bed is then wet, so it needs to be the CO2. Sorry, the water is blown out by hot air, and then the bed is dried and the capture can begin again. Okay. The other proprietary bit that they have is how they actually do the structuring. And so the structuring is actually stacked laminates. And so it's a carbon mesh that gets coated by the moth, the CAF20 in this case. And then there are little pimples of silica that are printed, and that acts to separate these. And you can control the thickness of the coating, you can control the size of the pimples that are giving you the separation. So this is what you between those two, you can moderate your mass transfer and your heat flow. These are pictures from the SANTE facility. So they managed to do this in a roll-to-roll manufacturing. So this is coating of moth. This is printing of the silica pimples. There is actually a robotic assembly that stacks. And then ultimately, here's the engineering manifestation. Now, so again, in going back to this word derisking, so I thought we had done pretty good stability testing, but obviously it's, if you're looking at making millions of dollars in development investment, you want to make sure what you've got is actually going to be stable. So this is one test that was done was 7 days of exposure, direct exposure to flue gas that had this composition. So this was a natural gas flue gas. Another test was done on the actual laminate, and this consists of a rapid cycle of 1 second of steam followed by 4 seconds of hot air to dry. And in both of these tests, the CAF20 lost under 2%. The steam cycling test was actually run for 24 days. So this is close to half a million cycles. So here we have Omid, who is SANTE's main sorbent expert, and Pierre is actually their vice president of research. So they've been tremendous partners in carrying this forward. So here's another test that was done. This is actually just testing with air. with hot air. But the comparison here, because in the SANTE system, after the system is treated with steam, you dry it with hot air. And so you have a comparison here between CAF20 and an amine modified sorbent, a chemisorbent. Now, if you talk to a lot of, I would say, easy comparisons, the first thing people will look at is, well, what's the working capacity? And if you compare a chemisorbent and a physisorbent, typically your chemisorbent is going to have a higher working capacity. It'll have a higher binding affinity, and it'll have typically a higher working capacity. But it's also a reactive, the amine is a reactive group, which can oxidize. And so this is 7 cycles of treatment with hot air under these conditions. So I guess a question I would ask is, if you wanted to compare the working capacity of the CAF20 and the amine, which cycle are you actually picking? Okay, so again, this is, there's many more metrics than simply capacity selectivity. When you actually go to a 30 ton per day scale, this is what their infrastructure looks like. This is not specifically one that was made for CAF20. This was actually made for an amine system. And so an important thing to also remember, even with this, it's not a drop-in solution, because the durations of the different steam, air, and drying will be very different for a physisorbent and a chemisorbent in this infrastructure. But just to give you an idea of the size and how far SANTE has actually come. So back in December 2020, I was really happy, because this was the very first time that SANTE, I think, publicly had said that they were put anything in press that they were using our material, and I was super excited with that. And so here's an interview with Lafarge Holcim and SANTE. So CL is Claude Letourneau, who is SANTE's president. And so he said, MOF CAF20 developed at University of Calgary. We knew relatively early on it was what we needed, but the cost was too high. In 2018, the researchers found a different way to make it, which lowered the production cost. So on that note, let me just introduce Roger and Jared. So they are 2 former PhD students who also stayed in the lab as postdocs to help commercialize this compound. And so they came up with a way basically to make them off at room temperature. And there were a lot of challenges. So we were literally making this in hardware store buckets. And this is a filtration sock that's used in the food industry. And ultimately, the limiting step for an ambient temperature synthesis just becomes washing, because there are some of the ligand is left in the pores, and you don't get the full capacity you would expect. So this is a recycling solvent system with a filter that we were using, and again, we didn't expect this to be scaled to multi-ton scale. This exact prep. The point was just to de-risk it and show that it could be made, that you could make kilo quantities, and you could make the same things you were making at the milligram scale. But as far as being able to make something on a large scale, CAF20 is wonderful. Oxalic acid and triazole are both commodity chemicals, and importantly, the metal in this is zinc, which is also widely used and not sourced unethically. The solvents are just water and methanol, but I think if you go to the Fundamentals of Absorption conference, I'm sure you'll see SANTE talking about even improved synthetic methods. Importantly, you avoid a solvol thermal synthesis. You can go to higher temperature. It just shouldn't be solvol thermal, because then it's a safety issue at big scale. Less obvious things here, just the ease of stirring, ease of filtration, things that on a small scale are never an issue. But as an example, we had initially made with zinc carbonate, and we thought, well, carbonate will release carbon dioxide, and on a big scale, you'd like not to have gas released in a preparation. So we switched to the zinc hydroxide. And the yield dropped dramatically just because it was so much harder to stir. So the CO2 release actually made the slurry so much lighter and easier to stir mechanically. Maybe an everyday analogy would be when you're adding baking soda to your pastries, you get nice fluffy pastries because of the CO2 release. Okay. But anyways, this is not the exact prep that has been scaled up by BASF. And so Stefan Marx has taken the reins of this at BASF. And in our science paper, we actually have isotherms of 3 million fold scale of batch syntheses. So Stefan has carried out now much larger than 300 kilogram batches. This was almost a year ago. And this is CAF20 sitting in the 55 gallon drums at SANTE. Right, so where is everything now? So even back in March at the GHGT conference, SANTE presented their plans for the next level of demonstration, which is a 1 ton per day capture using CAF20 from a cement plant, a Lafarge cement plant in Richmond, BC. Richmond is actually, it's where the airport in Vancouver is. It's essentially Vancouver. So here in this tent structure, you would actually see the rotary absorption bed. So just to give you an idea of scale, so here's a shipping container. So this is for 1 ton a day, and this is operating right now. I'll just go back with a little bit more about some of the stability before undertaking, but this is from the same paper. So this is a unit that SANTE uses to test at a 0.1 ton per day scale. And this was natural gas augmented with carbon dioxide to bring it up to the concentrations you would find in a cement gas. So cement uses natural gas combustion, cement manufacture, but you also have the CO2 coming off from heating limestone. And so that gets combined and you ultimately get a stream that's about 17% CO2. So with a stream that's exactly this composition at 1 ton per day scale, 0.1 ton per day scale, these are basically the flat lines show no change in productivity, purity, or the steam ratio used to cycle the capture and absorption with CAF20. What's interesting here, it says with guard and without guard, this refers to an activated carbon that was used. So I should say this is with typically there's a SOx scrubber before this, but this is with NOx. So there was an activated carbon guard to remove the NOx, but even when that activated carbon guard is removed, we still see good retention. And the hours here, this is 2,000 hours. So this is even running a couple hundred hours without the activated carbon guard. And the last thing, going back to this December 2020 Global Cement Magazine article, SANTE talked about a planned project for 2 megatons a year CO2 capture from a plant in Colorado, a cement plant in Colorado. And so they're saying we need a ton of moth for 30 tons of CO2 to be captured. So this is about 220 tons of material. And I have to say, I don't think generating that amount is going to be an issue by then. So let me just begin my little wrap up. So let's, something very important I want to discuss is the synergy of CAF20 with the SANTE process. So as I mentioned, their process is capture the CO2, steam treatment, and then drying, blowing out the water, and then cooling. So for the capture stage, of course, you need good CO2 capacity and selectivity, but of course, you also need your water and acid gas stability. When you go to do the regeneration, It's very beneficial to have the modest heat of absorption for CO2. And it means you can use less steam to regenerate. But of course, the MOF also needs to be stable to that steam. When it comes to drying, now the fact that the CAF20 has a hydrophobic quality, you now have a modest heat of absorption for water. And so it's less energy to dry. But you also need, if you're drying just by blowing air, you need the oxidative stability. And then for the entire cycle, fast kinetics are important. I didn't talk much about that, but you know, the SANTE structuring gives excellent kinetics, but CAF20, even as a powder, you can tell just by running the isotherms data points equilibrate very quickly. And of course, you need something to be scalable and it needs to be durable. So I'm showing all this why. So everything that I've highlighted in blue here, none of these are derived from the CO2 isotherm. And so I always get frustrated when I see anybody present what looks like a promising material. And maybe it has good CO2 capacity, or maybe it's got good selectivity. And someone will ask, well, what would it cost to capture a ton? Okay, so these are all things that that are critical to this process, but they are not conveyed by the CO2 isotherm. So going back to this solid sorbent carbon capture wish list, I just wanted to highlight that some of these things, of course, it's nice to have, it's important to have everything, but there are some elements where just being pretty good could be sufficient. So for example, if you don't have necessarily a great, well, the CO2 capacity and selectivity will be enabled by typically higher heats of absorption. So these things need to be considered in tandem, the regeneration conditions, as the selectivity and the capacity is a function of the regeneration. But also, something we don't talk about as much again is the kinetics. And so if you don't have high CO2 capacity, that can actually be offset by very, very good kinetics. So if something has great capacity but can't be structured, if it can't be structured efficiently, it's going to have very poor kinetics. And that will really offset that benefit. Okay, so as I said, there's Arvind has a very nice description for this. This isn't a sprint, it's a decathlon. So ultimately though, in this whole list, the two items that are non-compromisable are the stability and the scalability. And I think in a lot of the academic studies, they're kind of afterthoughts. So if you really want to take something into an industrial implementation and de-risk it for partners, these are things you absolutely need to be considering. This is my almost last slide. So I've talked about de-risking from the sense of what can someone making a new sorbent do to de-risk it going upstream, but this can also be, and it should be, a two-way street. So if there were some more accessible, smaller process testing opportunities, that would be very nice. And by smaller, I'm just kilo scale. Again, a lot of people who are doing the structuring, making the powders are not experts in, we could do maybe rudimentary structuring, but not something that will give optimal complex fluid dynamics. And in order to do that, really, it needs to be, you need to know knowledge of the exact process stream that's being targeted. So this is something where industry partners can really help. It's very important to assess materials under process conditions that are optimal for them. Don't write off. I had someone tell me once, because CAF20 wouldn't work in water, in actual liquid water, that it wasn't a good material. And a final comment: if you're really expecting a step change, don't necessarily expect it to be an easy fit with existing infrastructure. But I think this is a big enough problem, and there's enough potential investment that things can really progress from first principles through the entire chain. So with that, I'll just acknowledge the many funding agencies who've contributed here. Alberta Innovates is our provincial science agency, and they were very generous to myself and Arvind. GreenSTEM is actually a program for student entrepreneurs that helped Roger run a startup for a couple years and really develop the scale up quite a bit. And I'm sure SANTE would want to acknowledge the significant funding from the US Department of Energy. And I just want to, I've mentioned or shown photos of many of these people on the slides, but for me, this has been years and years of just sometimes frustration, but it's honestly gone so much farther than I ever thought would have been possible. And so my sincere thanks to everybody involved here. It's just been phenomenal to work with all of you. And my last slide, well, I didn't talk at all about climate change. I think with this audience, it's not necessary. About 3 hours from Calgary, we actually have an area called the Columbia Ice Fields. And so these are hundreds of kilometers of glaciers and ice from the last ice age. So the highway actually runs down here. And you can actually see, they have it signposted the recession of this particular glacier over the past decades. And you can really see, even in the last 20 years, how dramatically it has shrunk compared to the rest of the century. So with that, thank you all for your attention and the chance to give this talk.
Thank you very much, George, for your talk and your time. It was really great to see all of these results all in one place and to hear the story of how things went for you. And it's great to see a MOF being deployed commercially. We have some questions that have come through. There are also, by the way, for the people in Zoom, I should say, if you have any questions, please submit them via the Q&A tab at the bottom of your screen, and then I will read them out to George. As I mentioned, we have some questions that have come through kind of on the adsorption and material side. Before I get to those, I'll ask one on kind of the more commercialization side of things, considering that that was one of the highlights of this talk. Is there anything that you have learned in the process or tips for others or potential traps that people should be aware of if they want to follow a similar pathway for their material that you perhaps didn't expect before you started?
I think for us, the one thing that was the biggest frustration was when we knew we had this material that had this unique water competition ability, that it was the most stable MOF we'd ever made, but it might not be able to be deployed. Even though it could be made in one step, the fact that the one step was solvable thermal, that was potentially going to be a hurt. You could not be making this in 100-gram batches. So I think the scalability and the stability, those are critical. And I would say I underestimated how important those were. So really take the de-risking of those two very, very seriously. That would be my advice.
Thank you very much. Right, so we have a few questions from YouTube. One is from Bhubesh Balasubramaniam. Would changing the metal center give a similar or better performance than the zinc variant that is presently used?
I think well, first of all, changing the metal center would completely change the pore topology. And this very specific pore topology, pore size and shape, where you're having the CO2 suppress the water, I think that would change. But I also believe the zinc is very important for how stable this MOF is. I don't have a, if you were to just take the crystal structure and truncate it, you would be looking at a mix of where you truncated it, you might have a 5-coordinate zinc and a 3-coordinate zinc. The zinc centers are 5-coordinate. If these were other typical cheap transition metals, they would likely be octahedral. And I can't imagine that you would retain the hydrophobicity of the structure. I think you would be generating open metal sites that would be binding water, and it would completely change the properties of this compound. So I actually believe the outer surface, this MOF is flexible. There is a flexing that I didn't go into, but I believe the outer surface can actually passivate. And part of my reason for that as well, for thinking that, this was one of the hardest MOFs we've worked with to grow single crystals of. And so I believe it gets to a certain particle size and that outer surface passivates, but that would have to do with I'm sure that's critical for zinc. Zinc is a D10 ion. And so there's no ligand field preferential geometry. And so I believe it on the outer surface, I think we might have some 4 and 3 coordinate zinc centers, and that allow the surface to be passivated and not hydrophilic. So that was the long answer. The short answer is I don't think you would get exactly the same thing by changing the metal.
Thank you for the detailed response. I hope that answers their question. Related to actually what you spoke about in your response, which is changing the pore topology. How much scope do you think there is to adjust that while still maintaining the kind of hydrophobicity while increasing the CO2 interactions, the heat of adsorption? And I ask that because one of our next questions is from someone called Tristan Sim. And their question is, has CALF20 been evaluated for direct air capture, 400 ppm CO2?
Right. So I'll answer the direct air capture question. You can look at the isotherm and see the uptake at 400 ppm. So it's not very high. It certainly doesn't compare to, say, to the systems that have come out of Mohammed Adoudi's group. But having said that, there are people interested, absolutely. But I would say a serious look at it would be, again, optimal integration with an engineering form. And but my gut instinct is that it would be a challenge, just because the 400 ppm uptake is quite low. As far as changing the structure, of course, that would be, there's lots of people working on that, but it's subtle, and it is something where you need to consider cooperative competitive interactions to see the full benefit of the pore shape is only manifested in the competitive binding experiment. But I don't see an easy answer to that one, but I think it can be done.
Thank you very much. I guess related to that is, do you think there's any particular reason why MOFs like CALF20, UTSA 16, perhaps some of the aluminium fumarate style MOFs, which have these lower pore volumes, weaker water interactions, and that kind of thing, are they more difficult to synthesize, or have they not been particularly interesting for one reason or another? Like, why are we seeing fewer incidents of these MOFs as compared to all of the as you mentioned, the open metal site kind of family, enormous pore volume, that kind of thing?
Well, I think it's really just how the literature has developed. You know, I see, I sat through a seminar recently by an undergraduate student who was doing, not for my group, but for a different group, but directed readings on MOFs for CO2 capture. And I have to say, I disagreed with a lot of what the student ultimately concluded, but the conclusions were all based on what was in the literature. So, you know, there's certainly been periods where high binding affinity and, you know, larger pore MOFs were a bigger target for people. And I think it really, in terms of why the small pore ones aren't as targeted, they tend, it depends what metric you're looking at. I mean, if your metric is just how much CO2 is it taking up, the small pore MOFs typically will not take up as much. But if you want to strike this balance of the CO2 phobicity and the hydrophobicity, I think that's going to be much more likely in a small pore, where the impacts of the pore walls are more pervasive. So.
Yeah, thanks very much for that perspective. I think that's important for, personally, I think it's important for people to keep those things in mind. I appreciate that way of, we've come to the end of the hour. We have a question here from Arvind, which perhaps will be the last one. And he asks, the water CO2 competition that we see here, is that also seen in any other systems?
So I've only seen one other example, but there weren't really details of how the experiment was done. So I don't want to really, well, so short answer, no, I'm not aware of one, Arvind. Not actual suppression of water. Yeah.
Great, thank you very much. Thanks again for taking the time to give this presentation and this small Q&A session that we've just had and discussion. With that, I'll hand over back to Nicholas Wilkins, who will wrap up the session and give some details of the upcoming webinars.
Thank you, George Shimizu, for your presentation on de-risking metal organic frameworks for industrial scale carbon dioxide capture. We also thank all of the attendees for joining this webinar, and we hope that it was both educational and enjoyable. An edited version of this webinar will be posted to the IAS's YouTube channel with an announcement on the IAS Twitter feed. The hope is that the work discussed today will be a useful resource for the adsorption science community in the future. The next IAS webinar will be given by Alexander Nymark on March 8th. Announcements regarding the next webinar and other IAS online events will be posted on our Twitter feed and through the IAS mailing list. With that, we thank you for joining us, and we hope that you will join us again soon.